Okay, we're going to get into how we're going to abbreviate these. So listen, the reason why we're going to focus on our noble gases is because the noble gases have complete outer energy levels where all of their 8 electrons have been filled in. Every noble gas you'll find ends with 8 electrons, with the exception of helium, because helium only has 2. Okay? So we're going to add in where our noble gases are because they have the perfect electron configurations that every other element actually kind of wants to mimic. So they're the perfect elements of our periodic table. So above your 1s, you're going to put He for helium above the 1s2 because helium fills in the 1s2 sublevel. Now, above the 2p, above 2p6 is Ne for neon. Above the 3p6 is your Ar for argon. Above the 4p6 is Kr for krypton. Above the 5p6 is the Xe for xenon. And above 6p6 is Rn for radon. We're going to ignore oganesson, number 118, because it's the last thing on the periodic table. And we're not going to use this for abbreviations anyway, because it's the very last element. So we're going to ignore it. Okay? So we've got our helium, our neon, argon, krypton, xenon, radon placed on your diagram so that you'll be able to easily use it. So we're going to follow these rules to abbreviate our electron configurations because we want to write as little as possible in chemistry, I would say. Don't you agree? Like the least amount of writing you can get by with in a day is always the best. So we're going to follow these rules. We're going to use chlorine as our example. You guys already mapped chlorine out today. When you mapped chlorine out today, it looked like this. 1s2, 2s2, 2p6, 3s2, 3p5. That took a little while to write. So now we're going to learn how to abbreviate it. So it says we're going to pick the noble gas that is closest to the element but smaller in number. Like obviously argon is right next to it, but it has one more electron. It's bigger in number. So we have to go with neon. So to abbreviate, we're going to put neon in the parentheses. Okay? So that's step 1. Put the noble gases symbol in the brackets. This notation is telling chemists that we have 10 electrons already assigned, just like neon has 10. Okay? So step 2 says subtract the noble gases atomic number from your element's atomic number. Chlorine's number is 17. Neon is 10. 17 minus 10 means I'm going to have 7 electrons yet to assign. So now I just pick up on my diagram where I left off. This is where neon is. It filled up through 2p6. I got to assign 7 more. So I'm going to do the 3s2, and then I'm going to come down and I'm going to do the 3p5. So now I'm done. Okay? So that shows me this is my unabbreviated versus my abbreviated version. Okay? So I essentially got to take this front portion out. That was my neon through the 2p6. All I added was the 7 electrons that follow the neon. Does that make sense? Okay, you'll notice that you're still ending at the exact same spot. You're still ending with the 3p5. You want to be ending the same way you would have ended on the unabbreviated version. So that's kind of a way to double check yourself. On some periodic tables, like you guys, I'm sure can't see it from where you're sitting, but on that wall periodic table, above every element is its abbreviated electron configuration. Some periodic tables will include that for you, which is kind of nice. Because, why do we love electrons? Why are we loving electron configurations? A way to show what we're talking about. Why are the electrons so important? Yes, because they are going to be where our bonds are formed. And we haven't got to the bonding yet, but that's the next unit, and that's going to be so important. So we are loving these electrons because we want to know how many electrons are paired, how many are unpaired. Like if we were looking at this 3p5 here, and we wanted to know how many electrons were paired versus unpaired, we would have this one little spot, this one last orbital where we could take another electron. And you'll find out, oh, chlorine, it can make one chemical bond. So that's kind of cool. We'll learn about that as we progress this year. Okay? But we love the electrons and we want to know where they are and what shape they're spinning always, because it is going to affect what kind of bonds we can make. All right, so we're going to do radon next. Radon is a noble gas. It's at the very next to last noble gas. It's in period 6. So you're going to look at radon and you're going to say, all right, it's got 86 electrons. Now, we have to follow these same exact rules even if what we're assigning is a noble gas. Because I know you would love to just put radon symbol in the bracket and say, I'm done, right? I don't want to do any math to figure out extra electrons. But you're not allowed to do that for a noble gas. For a noble gas, you're always going to back it up to the noble gas that was lower in number than it. So when you look at xenon, we got to put xenon in the brackets. What's xenon's number in your periodic table? 54. 86 minus 54 means how many electrons do we have left to assign? More than 2. We got a 2 here. 6 minus 4 is 2. 32 extra electrons. I'll take assigning 32 electrons any day over doing the full 86, right? So, here I was at xenon, took me through here. I'm going to assign 32 more electrons. So I'm going to go to 6s2. After 6s2 is 4f14, 5d10, and then 6p, I get all 6 because radon filled the p sublevel. So if I add 2 plus 14 plus 10 plus 6, you'll find out that's 32. It's right where I wanted to be.
So one thing I did not get is why do you do 4F and then 5D when you're in the 6th row?
Oh, okay. Because that Alfvell principle said we always fill the lower energy levels first, and the 4F comes in long before the 6P. That's why we're filling or using this diagram, because this keeps the sublevels in the predictable manner, okay? As long as we always fill from the right side through the left side of the arrow. When we need more than, say, the 56 electrons, we bump down to the next arrow. We have to start with the 4F first, then we go to the 5D, then we go to the 6P. And you weren't here yesterday when we kind of talked about playing the periodic table. like a board game and doing it with this block scenario, but you can actually fill it in order using this block formation. And there is a YouTube video on Canvas about that, but we wrote down here that we had to remember, once we filled in our 6S2, we had to bump down to the 4Fs, fill in the 4Fs next, because this is supposed to be squeezed in, this whole row is supposed to be squeezed in ahead of the 5D. It's like squeezed in right here. So we go 6S, 4F, then we can fill the 5D before we go back to the 6P. So it's just kind of, it's just one of those tedious things. Okay. And like if you wanted to write all of these out, like on the YouTube video, something that they did was, you know, they would write in, this is 2P, 3P, 4P, 5P, 6P, 7P. You can kind of write in each of those, 3D, 4D, 5D, 6D, 4F, 5F, and so forth, okay? But it's just that 4F has lower energy than does the 5D, so we always fill this one first, bounce to the 5D, then we'll bounce back to the 6s. So things get a little muddled as we go. And that's why either using this diagram or using the periodic table make it a little easier to keep track of them. Which level is slightly lower energy than the others. Okay? So we've done two of them. Should we do one more? Let's do one more. You guys can map it out on yours. If you want, let's do zirconium. It's number 40. ZR number 40. Oh, this is really nice. I was really nice to you because there's a noble gas super close to it. You're hardly going to have to assign any at all. But so, which one are we going to put in brackets? Which noble gas? Kr. And krypton takes care of how many electrons? 36. 40 minus 36 is 4 extra electrons that you have to account for. So you're going to go to your 5s2, and after my 5s goes my 4d.
8.
2 plus 2 is 4, but we only want 4. So that's a super easy one for zirconium, correct? All right. So are we kind of getting the hang of how to abbreviate them? It's super easy. It's probably way more fun than those long unabbreviated ones. Okay? So I'm going to show you a couple other things on your periodic table. All right. This is just kind of a nice tally of how many electrons are in each sublevel. Okay? Each quantum number has an equal number of orbitals. So you notice, like in the 1 level, we only get S's. In the 2 level, we get S's and P's. In the 3 level, S's, P's, and D's. Okay? I want you to look at your periodic tables, and you're going to use chlorine as our example. Okay? So when we look at chlorine in the upper right-hand corner, on this Army periodic table, this gives you the electron configuration notation of how many electrons are in each and every sub-level. So we look at chlorine has 2 in the first sub-level. So those are those 2 right there. In the second level, it has 8 total, 2 plus 6, that's my 8. And in the third level, it has 7 total, because 2 plus 5 is 7. Okay? This information is going to be super handy for you in interpreting where your electrons are, and particularly tomorrow we're going to be learning all about valence electrons and how to pinpoint those. Okay? So you do have this electron configuration notation found there. This Army periodic table is one of the only periodic tables that will give you that info. And it's super handy for this unit. It'll be super handy for you if you take college chemistry one day, which, you know, my job is to get you prepared that you could pass a college chemistry someday. So, you might want to keep track of these periodic tables. Try not to lose them between now and then, because that information is going to be super handy. So we could pinpoint any element. So find mercury. It's in the pink. It's number 80. It's number 80, and I want you to tell me how many electrons does it have in the 4th energy level. So at energy level number 4, how many does it have? Carly says it's got 32. She counted down 1, 2, 3, 4, found her 32, right? That's easy. The 4th level is maxed out at 32, okay?
That is not
Does it have any in the 5th energy level? Yes. How many are in the 5th energy level? 18. How many are in the